We are going to learn about inverse hyperbolic functions and then walk through some examples. Since hyperbolic functions are defined in terms of exponential functions, inverse hyperbolic functions are defined in terms of logarithms. I've written down the definition of inverse sinh of x, inverse cosh of x, and inverse tanh of x. All three of these definitions have logarithms in them. And then one thing to note with these definitions is that each of these functions has different domains. Inverse sinh of x is defined for every value of x. Inverse cosh of x, because of that square root of x squared minus 1, is only defined if x is greater than or equal to 1. And then inverse tanh of x is defined between minus 1 and 1, and that's because what's inside our logarithm here has to be greater than 0. Let's now walk through some examples where we are going to find the numerical value of each of the given expressions. The first expression that we're given is inverse sinh of 1. Let's start by writing down the formula for inverse sinh of x. Inverse sinh of x is the natural log of x plus the square root of x squared plus 1. Now what we're going to do is we're going to take x and let it be equal to 1. So we have inverse sinh of 1 is natural log of 1 plus the square root of 1 plus 1. And this is the natural log of 1 plus the square root of 2. If you put that into your calculator, you get an approximate value of 0.8814. This is our exact answer, and then this is the approximate answer. Now we have a really similar example for number 2. We are going to evaluate inverse cosh of 1. Let's begin by writing down the formula. Inverse cosh of x is the natural log of x plus the square root of x squared minus 1. Now we're going to let x be equal to 1. So we have inverse cosh of 1. This is natural log of 1 plus the square root of 1 minus 1. So we end up with natural log of 1. Natural log of 1 is equal to 0. Now let's look at our third example. We are going to evaluate inverse tanh of 0. Let's write down our formula first. Inverse tanh of x is 1/2 times the natural log of 1 plus x, all divided by 1 minus x. Now let's let x be equal to 0. So we have inverse tanh of 0. This is 1/2 natural log of just 1 plus 0. So we have a 1 on top, and then we have a 1 on the bottom. So this is 1/2 natural log of 1. Natural log of 1 is 0, so our answer is just equal to 0. Let's now look at how to find the derivatives of inverse hyperbolic functions. These formulas are different than the derivatives of inverse trigonometric functions. I've written down the derivative of inverse sinh x, inverse sech x, inverse tanh x. Sometimes I feel like those are really hard to say. And then inverse cosh x, inverse cosh x, and then lastly, inverse coth of x. Before we walk through our examples, I want to call your attention to this formula and this formula. Those two derivatives are the same, and that might seem a little strange, but it works out because the derivative of inverse tanh of x is only defined for absolute value x less than 1, and then the derivative of inverse coth of x is only defined for absolute value x greater than 1. Let's now walk through some examples where we're going to use these formulas to find the derivative of the given function. The first function that we're given is f of x is equal to inverse sinh of tangent x. Let's begin by writing down the formula for the derivative with respect to x of inverse sinh of x. That is equal to 1 all divided by the square root of 1 plus x squared. We are going to need to use the chain rule because we have an outer function and an inner function. Our derivative f prime of x is the derivative of the outer function. That is 1 divided by the square root of 1 plus x squared. X is what is ever inside, and in this example, what is inside is tangent, so we have a tangent squared x in our square root. And then we have to multiply this by the derivative of what's inside. The derivative of tangent is secant squared x. Now we can go ahead and do some simplification. We have an identity that tells us that 1 plus tangent squared x is secant squared x. So in our square root, we're going to put in secant squared instead of 1 plus tangent squared. So we have the square root of secant squared x times secant squared x. So one of our secants is going to cancel, and we end up with just an answer of secant x. Let's now look at our second example. We are going to find the derivative of inverse cosh of the square root of x. Again, we are going to use the chain rule because we have an outer function and then we have an inner function. Let's first write down what our derivative is. The derivative with respect to x of inverse cosh x is 1 all divided by the square root of x squared minus 1. Our derivative f prime of x is then 1 all divided by the square root. Our x is now root x, so we have the square root of x quantity squared minus 1 times the derivative of root x. So let's just write this as the derivative with respect to x, and we'll write root x as x to the 1/2. Our denominator is the square root of x squared, so that's just an x. So we have the square root of x minus 1. Now we can take the derivative of x to the 1/2. This is 1/2 x to the minus 1/2. So this gives us 1 all divided by the square root x minus 1 times 1. And we can write our x to the minus 1/2 as 1 over root x. So we have 1 over 2 root x. And now what we're going to do is we are going to combine this square root with this square root. And we're going to write this as 1 all divided by 2 times the square root of x times x minus 1. And that's our answer. Hang with me. We have one more to go. We are going to take the derivative of inverse coth of secant x. We're going to use the chain rule again. Here is our outer function, and here's our inner function. Let's write down what our derivative is. This one is actually easier. The derivative with respect to x of inverse coth of x is 1 over 1 minus x squared. So we can say f prime of x is 1 divided by 1 minus, and then the x is whatever is our inside function, which in this case is secant x. So we have 1 minus secant squared x in our denominator. And then we're going to multiply this by the derivative of secant x, which is secant x tangent x. Just going to draw a line here so we can see the right side from the left side. I think we might be able to simplify this. So I'm just going to write down the formula that I memorized. 1 plus tangent squared x is secant squared x. I always write down what I've memorized and then I rewrite it in terms of what we need. We need 1 minus secant squared x. So 1 minus secant squared x is minus tangent squared x. So that's what we can put in for our denominator. This gives us 1 all divided by minus tangent squared x, and then we have a secant x tangent x. So our tangent x is going to cancel, and then we're left with minus secant x all over tangent x. Secant is 1 over cosine, tangent is sine over cosine, so our cosines are actually going to cancel. So let's write this as minus 1 over cosine x on the top and sine x over cosine x on the bottom. And then we'll cross out our cosines because they cancel. So we have left minus 1 over sine x, and that is minus cosecant x.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.